Dear friends, this presentation is dedicated to the pulleys and systems made by their combination. The pulleys are used for lifting weights, like displayed in the picture, or for creating great forces by means of small forces. We see how they work and how to calculate the lifting force case by case. This time the theory is little. There is not much math behind. We will have many experiments instead. Let's see. We start describing what is a pulley and what is a hoist. Then we will see the simple hoists made by unique rope and many pulleys. Soon after we make an experiment assessing the lifting force. Then we display the multiple hoists made by many pulleys and few ropes. The following three experiments are clarifying how they work and their limit of operation. The last part of the presentation is dedicated to a special type of hoist called differential hoist. We will see all the details in the coming slides. The pulley is a free wheel rotating on an axle, having a groove for guiding a rope, and the axle can be fixed or mobile. The task of the pulley is to change the direction of the rope, also to change the direction of the lifting force. The mechanical advantage MA is defined as the ratio between the load and the effort. If the axle is fixed, the effort equals the load. If the axle is mobile, the effort is 1/2 of the load, as displayed in the picture here aside. What is a hoist, also called block and tackle? A block is a set of pulleys assembled so that each one rotates independently from the others. Two blocks with a rope attached to one of the blocks and threaded through the two sets of pulleys form a block and tackle, hereafter called hoist to make it simple. The task of a hoist is to change the pull direction and increase the mechanical advantage. The mechanical advantage must be calculated case by case. See afterwards. How to calculate or meter the mechanical advantage? To calculate it, we need to find the effort by knowing the load and the shape of the hoist. Three rules. Number 1. Since it is not possible to transfer any mechanical moment because the axle is free, there is no brake or motor, then the tension in the rope must be the same for each of its parts. This force is equal to this force. Number 2. The force at the axle is the vectorial sum of the forces of the rope. If the forces are vertical, like in the example, or if they have some direction, then this force applied to the axle is the double. Number 3. The sum of the forces to any section of the hoist must be equal to 0. So if we take the section in the example and we apply the equilibrium, we find the effort being 1/4 of the load. To meter the mechanical advantage, we have two ways, a direct and indirect way. The direct consists in measuring the effort by a dynamometer. The indirect to meter the displacement instead. This time we need to meter two displacements, both for the load and for the effort. The principle behind is the conservation of mechanical energy, and it can be applied if no friction or losses. However, we remember that the mechanical advantage is a theoretical value. There is a general rule that the mechanical advantage of an ideal block and tackle is N, where N is the number of sections of rope that support the moving block. In the example, we have 4 sections, 1, 2, 3, 4, so the mechanical advantage is 4. With the first experiment, we want to demonstrate both that a hoist made by 2 pulleys, like in the figure A, has a mechanical advantage of 2, and that a hoist made of 4 pulleys, like in the figure C, has a mechanical advantage of 4. As equipment, we need 1 water canister, 1 dynamometer, 1 rope, 4 pulleys, and 1 tape meter.
We start now first metering the weight of this water canister with a dynamometer. Let's say 5 kilograms. Okay? Now we have put 1 pulley up, 1 pulley down, and we meter the force needed to lift the canister. Let's say more or less 250. The half of the weight of the canister. Now we have added another pulley up, another pulley down, totally 4 pulleys. And we meter the force for lifting it. Should be 125. Actually, 1/4 of the load is a lift needed for that. Eventually, the force is divided by the number of pulleys. Totally we have 4. There is another way to meter the force for lifting the canister, to have an indirect metering. Instead of the force, we meter the displacement. And this displacement, we know, should be in the inverse ratio respect to the force. From the tip of the ladder up to the bottom, there are 2 meters. Let's meter now how much will be lifted the canister. They are exactly 50 centimeters. Therefore, we demonstrate that the ratio between the forces is exactly 4.
Is it possible to increase further the mechanical advantage? We have seen that the mechanical advantage is more or less equal to the number of pulleys. Therefore, if we want a value of 8 or 10, we should use many pulleys. And this is complicated. There is another way to increase the mechanical advantage without increasing the pulleys. That is to use small ropes. In the example 1, we have 4 pulleys and 2 ropes. One rope is driven by the pulleys A and B, and the second by the pulleys C and D. The mechanical advantage of this hoist is 6. In the example 2, we have still 4 pulleys, but 3 ropes. One for pulley A, one for pulley B, and one for pulleys C and D. The mechanical advantage in this case is 8. In the experiment 2, we want to meter the mechanical advantage of the hoist at example number 1.
Now we make this trial. There are 2 pulleys up, 2 pulleys down, and 2 different ropes. As per the schematic that we have seen, we should have a mechanical advantage of 6, okay? And how to meter it? We pull this rope from the top of the ladder up to the bottom. They are exactly 2 meters. And we meter how much will be lifted the canister. If our calculation is correct, should be exactly 1/6 of 2 meters. They are 33 centimeters. Also, the mechanical advantage of this hoist is exactly 6.
In the experiment 3, we want to meter the mechanical advantage of the hoist at example number 2.
The last trial we want to do is with another type of hoist, having always 4 pulleys, but this time 3 ropes, 2 times the red one and once the blue one. This hoist has a mechanical advantage of 8. Let's meter it. The canister gets lifted of exactly 25 centimeters, that is 1/8 of 2 meters.
Some consideration on the past two trials. Looking at example 1, we observe that we cannot raise the load till to the fixed block whose travel will be h. That's because the pulley C is traveling at a speed 3 times the load speed. Therefore, it will reach the fixed block when the load has covered the travel of h third. With similar considerations, we say that the hoist of the example number 2 has a lifting travel limited to h fourth. This limitation we didn't face with a simple hoist instead. With experiment 4, we want to visualize the issue described in the previous slide with reference to the example number 2. As you can see, the lifting travel is very limited. Let's resume here our findings. With a single hoist, the mechanical advantage is equal to the number of sections of rope that support the moving block. More or less, that is equal to the number of pulleys, n, at least if the pulleys are many. The whole lifting travel is achievable, but we need a very long rope that is n times the lifting height. With a multiple rope hoist, the simple rule is not valid any longer. We can get much greater mechanical advantage with same number of pulleys and many ropes. The problem is the lifting travel limitation. What would we like to have, should we can? Just imagine an ideal hoist. Very high mechanical advantage with less pulleys, no lifting travel limitation, and short rope. Am I just dreaming? Not at all. This hoist does exist. Its name is Differential Hoist. Let's see it together. What is a differential hoist working principle? It is operating by pulling the slack section of a continuous chain that wraps around two pulleys joined on a common shaft. The two pulleys rotate simultaneously and they are fixed together. The load is applied to the axle of a third pulley that is lifted by the same chain. To find the mechanical advantage, we need the rotation equilibrium of the upper pulleys, considering that x is 0, because this side of the chain has no load, therefore zeta times capital R, where capital R is the radius of the bigger pulley, plus y times R, R is the radius of the small pulley, equals W times capital R. The rotation equilibrium of the lower pulley says Y equals W. And the translation equilibrium of the same pulley says Y equals load divided by 2. Therefore, we can get this expression, and finally, we find the mechanical advantage as 2 times capital R over capital R minus R. And by using the number of teeth of the sprockets, we can write a similar formula replacing capital R and R with capital N and N respectively. With such hoists, it is common to achieve a mechanical advantage of 30 or even 50, and that using only 3 pulleys. If you don't believe me, I challenge you. Please build it yourself and try. I hope you have enjoyed my presentation, and do not forget to tell me your observations. See you next time. Bye bye.